Well, I was reading all of these stories, and I found a story, and it's circulating on the blogs now. There's a story from a guy who works at MIT, and he explains how a nuclear power plant works. Now, I want you to know he's not a nuclear scientist. What is he, Tiffany? What kind of scientist is he? He's a mechanical engineer. The reason why he wrote this blog that is everywhere is because he has family and friends over there, and they were all freaking out. And so he did his research, and he said, look, here's how it works. I want to explain this to you real quick. There are 3 lines of defense in this, and I'm going to explain this a little easier here. In just a second. I'm going to, of course, use M&Ms, and that will, of course. Okay. Here's the first line of defense. It's this outer shell, and this is what you saw explode, and I'll explain it in a second. That's what you saw explode. Then these are the nuclear rods, and this is actually a line of defense because they're not rods, they're actually... Well, I'll show you with the M&Ms in a minute. And then this is what makes the steam. Here's water. And this is what makes the steam. The rods and the water. It boils the water. And then it's in this containment facility like this. And this is the last line of defense. It's all cement. Now, let me show you how this works. To show you how much more has to go wrong. First of all, this power plant shouldn't be standing today at all. It wasn't equipped, it wasn't built to withstand a 9 on the Richter scale. This is 7 times more powerful than what this plant was designed to handle. But it's still standing. It's a miracle that it is. So, here's what you have. First of all, you have the nuclear fuel. They're pellets. And they put them all together, and they put them in these rods, just like this. It's a colossal waste of M&Ms, but I get most of my energy from them too. Then they're put into, this is the core. They're like this, they're put together. And they're put in here, and this is where they kind of do their magic, and they boil the water. So now this is the core. The core is in this facility, containment facility. I'm going to have to take these M&Ms out. Darn it. The 5-minute rule. Anybody eats those M&Ms besides me, I break your hands. So they're put in here. Water is put on. And then this is sealed. This is where you get the steam. It's like a pressure cooker. And this is why I'm not a nuclear scientist, because there's no way I can close that. Then they cover this all with concrete. And then they build the outer shell. Now, what has happened? Well, first, because it was boiling, and a pressure cooker has the steam coming out, which it's supposed to, they needed to relieve some of the pressure so the whole thing didn't explode. They relieved the pressure in here. When you saw this footage, show the video up here. When you saw this footage of this explosion right there, has anybody explained to you really what that is? That is the steam coming in here mixing with hydrogen, and I can't explain it. I mean, I'm the guy with the M&Ms on the show. But the steam coming out, that is this happening. This outer shell blowing. This isn't a sealed containment. This is like the last line of defense. This is what you have to worry about. And this, remember, is impossibly sealed. This has the containment of the rods, which is the first thing to melt down. Then it has this. Then it's also contained in concrete. Let me show you. The rods will eventually break down when the water level, this is what's happening here, the water level should be up here. When they say that the rods are partially exposed, it's because the water is boiling out and the steam is coming out. The steam is supposed to be recollected in this facility, brought back out, cooled, and then pumped back in. But because there's no electricity, it couldn't pump it back in. So the water level keeps going back down, and the steam is just going out into the atmosphere. As these rods are being exposed, it gets worse because then the steam is exposed to this. Got it? The rods will break down, the water will go away, and so they'll be left with this iron or steel and concrete bowl. The theory is that concrete and steel bowl can stand up to like 5,000 degrees Celsius. This burns at 3,000 degrees. So far, everything has worked beyond what it was supposed to do. It's so stable at this point. Remember, 7 times more powerful of an earthquake than it was supposed to even stand. You still have this. If everything works the way it should, this can sit there forever and burn forever, and it won't be a problem. Now, could something go wrong? You bet. Yeah, it already has. There's an earthquake that was 7 times the power that it was supposed to have. So it could go wrong. But let's look at this now again with perspective. Let's say everything melts down. Everything goes wrong. What happens? Well, you've got most of the people out already. They've got everybody out within the 12-mile radius. That's what they say. So here's the meltdown. Let's just say worst case scenario, 12 miles, because it cannot explode. Remember, it can't turn into a nuclear bomb. It will kill 210,000 people. That's if there were still 210,000 people here. 210,000 people. A nightmarish tragedy, right? But that's if, assuming all of the people are there, and all of the containment doesn't work.